it till the your electric flux was done and Gauss theorem was done, right? So see, Gauss theorem has its applications. So that is continuous charge distribution. You need to understand it before you go with the derivation. So class, it is very simple. Continuous charge distribution means how your charge is distributed over a surface. Like if I have a straight wire, so how is the charge present on this wire? If I have a plain sheet, then how the charge is distributed on this sheet? If something is like a sphere, so what is the amount of charge that is distributed in each section of it? This is what is called as linear charge density. The first one, linear charge density, is for the one dimensions. Now, linear term is related to something which is related to your length, longitudinally linear. So if I have a wire and charges are present on the wire, then I'll say the total charge per unit length is what is meant by the linear charge density. See, this linear charge density is represented by the symbol lambda. This is how it is represented. Now, what is the meaning of it? It basically means that whatever is the total charge present on a length. So Q by L is the full formula for it. What is Q? Q is your charge. L is the total, and that has been already written here. This symbol is the linear charge density. But remember one thing, this is valid if your charges and length and everything is constant. Constant, please. If your charge distribution is constant, means it's uniform. Length is constant, charge is uniformly distributed. But if you get questions where your charge is not uniformly distributed, then you can use lambda is equal to dq over dl. Means you differentiate it with respect to length. dq means you are performing differentiation.
When are we supposed to use differentiation?
If it is variable, like I am giving you there the value of lambda is, let's say, 3x square. So you are able to see that yes, x is a value which is the independent variable, and if we change the value of lambda can change. So this is when you have the variable linear charge density. So you will yourself see the terms like time will come, x will come, it will not be fixed. Or if you see length is variable, like dl is given as 3x plus 2x, like this. 2x squared, like this an equation is given for length, where you can analyze, yeah, this is not variable. If I give you the charge constant, let's say 3 coulomb, and I give you the length constant 1 meter, so you can easily divide it and you can analyze it that yes, these both are constants. So this is when how you have to identify. I'll show you a question also based on this. Based on linear, at least we'll do 2 questions and then we'll move on to the next one. Like, let me show you a question. This says a charge of 10 coulomb is uniformly distributed over a length of 5 meters. See, what is the linear charge density? Linear charge density means charge per unit length. So lambda will be equal to charge per unit length. Charge is given as 10 coulomb, length is given as 5 meter. So lambda becomes 2 coulomb per meter. Okay, lambda is equal to 2 coulomb per meter. That's it. See, you could analyze here that the charge, yes, it is constant 10 coulomb. Length is fixed 5 meters. So when you will divide it, you will get a fixed ratio. Now it is saying, the second part is saying charge on 2 meter length of wire. This is also constant. This also does not have any x, y, z in your answers. This is also constant. Then how will you get it? Because you don't have any equation separately for that. So when it is saying 2 coulomb per meter, we'll go to the definition of this. What it's written over here, 2 coulomb per meter means we can say that in 1 meter, how much charge has been distributed? Linear charge density means how is the charge distributed on your wire? On your straight wire, how is the charge distributed? A straight line is there, how is the charge distributed on it? So in 1 meter, if we take how many charges are present? We've calculated 2 coulomb. So in 2 meter, how many charges will be there? Simply 2 into 2, that is 4 coulomb. So you apply the unitary method over here and your answer will be there, because you cannot differentiate here. This is not variable. Length is fixed 2 meter. Lambda is also coming constant. I'll show you a question where you will see the variable values are there. But first tell me, is it clear to both of you till here?
Yes, ma'am.
Okay. Marwa, to you too?
Yes, ma'am.
Okay, please write it.
I'm done. I'm done.
Okay. Let us look one more question where your lambda is variable. See, this is saying the linear charge density of wire is lambda is 2x. Now you can see if the values of x will change, x is 0, x is 1, or x is something, and then you keep on putting the values of lambda, it was not possible. Why? Because your 2x, this is your independent variable, and lambda is the dependent variable. So here we can see that yes, this is variable. So lambda is equal to dq over dx, right? Charge per unit the length. Now on which length? On 10-meter length. We have to find the charge. So from this equation, if I want to get the charge, I need to multiply lambda with x. So see, dq is equal to lambda into dx integral. Okay. So Aisha, pay attention. You were having some confusion with this, though we'll do integration separately also. But just for this question, just pay a little attention. Charge is from 0 to 10-meter length. And this is, we are differentiating length only. Dx is what? Dx was the length. So 0 to 10. Now I'll put the value. Lambda is 2x. So here it will be dq's integral is q will be equal to lambda is 2x dx from 0 to 10. Now look, just a brief of integration right now, quickly I'm doing, but in detail we'll do it again. When you have a charge, or whatever is the value of this charge, or let's say a polynomial function, x to the power n is there. You write this as x to the power n plus 1. First step is this. And then you divide it by n plus 1. So here 2 is a constant, x has the power 1. So 1 plus 1. 1 is there, 1 plus 1 divided by 1 plus 1 from 0 to 10. So look, 2 into this is x square from 0 to 10 divided by 2. This 2 gets cancelled. Now you put the upper limit first. After this step, in place of this x, you put the upper limit first. So upper limit will be 10 square minus the lower limit is 0 square. So what's the charge finally? 100 coulomb. Is it clear, or should I repeat any step? Aisha, you've understood?
Yes, ma'am.
Okay. Marwa, you too?
Yes, ma'am.
Okay, write down this question, then we'll see other charge densities.
Ma'am,
Yes, Aisha.
ma'am, I understood everything, but after the third step, like after you integrated,
Mm-hmm.
then how did 2x come?
This step,
No, on top, on top.
this one.
Yeah.
Oh, see, lambda's value is 2x. So lambda dx. So I just put the value of lambda. So 2x dx.
Oh, okay.
Okay.
Mm.
Written?
Yes, ma'am.
All right. Now see, we have the next as superficial charge distribution. This is in 2 dimensions. So 2D comes when you have plane surface, area is spread. For straight lines, you have linear. For superficial, it means you are having area. So it is represented by this symbol, sigma. And it's very simple. See, sigma will be charge per unit the surface area. This is what is meant by the value of sigma. So this is again, see, same thing. Now we'll not be doing the questions again, but it's the same thing. If it is constant and if it is variable in any ways, you're going to write it as dq over ds. This is when it is variable. So simply your surface charge density is what it is, the charge per unit area. Now let's see one easy similar question to this constant part. A charge 10 coulomb is uniformly distributed on the surface of a sphere of radius 2 meter. You have to calculate its surface charge density. So surface charge density is charge per unit area. What's the area of a sphere? Surface area of a sphere. Marwa Aisha?
4 pi r square.
4 pi r square. Very good. So this will be Q by 4 pi r square. So 10 coulomb divided by 4 into pi, radius is 2 meters. Right? So 2 meters becomes 2 square is there. So 4. So this becomes 2 into 5 into 4. So 5 by 8 pi coulomb per meter square. Now charge on 2 meter square of fire. This means if we have sigma as 5 by 8 pi. So again, you will have to apply your unitary method. Unitary method says that in 1 meter square, you have 5 by 8 pi of coulomb. Right? So here when you will have it for 2 meters square, you will just have to double it. 5 by 8 pi into 2. So that becomes 5 pi 4 pi coulomb. So this much coulomb of charge in 2 meters square. So you calculate for the unit, you'll have every data with you. For anything you can calculate. Write down this one also.
I'm done. I'm done. I'm done.
Okay, last one that is left is volume charge distribution. So very simple. See, when the charges are accumulated inside any surface, then you cannot describe it with the help of its surface area. You need to describe it with the help of volume. So this is represented by this symbol rho, and rho is equal to charge per unit volume. So this is now again repetitive and easy. This is for a constant. And rho will be dq over dv if this is variable. Okay, like if you have, look at this, a charge of 10 coulomb is uniformly distributed throughout a volume of radius 3 meter. So when we are talking about rho is charge per unit volume. What's the volume of a sphere? Volume of a sphere? 4
4
by
by
3
3?
pi r. Yes,
Okay.
Q is 4 by 3 pi r Q. So this will be 3 Q by 4 pi r Q. 3 into 10 by 4 into pi into r is 3. So 3 Q. So 1, 3 will cancel this, make it square. 2 into 2, 2 into 5. So we'll get 5 by 3 into 3, 9, 18. 5 by 18 pi coulomb. Now, same thing you have to calculate on a 3 meter cube. So, second part says that if in 1 meter coulomb per meter cube, sorry, if in 1 meter cube you are having the charge 5 by 18 pi. So in 3 meter cube, you will get 5 pi 18 pi multiplied to 3 times. So that will be 5 pi 6 pi. Okay, so similar method, same thing. Now we'll start with the applications after this. Please write it down.
Mhm. Ma'am, done. Mhm. I'm done.
Okay, look class. Now that completes with the charge distribution. In the assignment, I'll give you questions based on that. And I'll give you the questions that are not using your integration. So you'll not have trouble, but some of the questions will be a little difficult, okay, from continuous charge distribution. They're not exactly difficult. If you go step by step, you will be able to do. So why will I give that? Because then in the next class, we can have a discussion on it. Because those are some important questions that will thoroughly clear your concept. What is the meaning of each of it? Because class, it is used. This is actually applicable and used a lot, especially this surface charge density sigma, even lambda, rho volumic one is used less in your CBSE board exam. In your entrances, NEET and JEE, rho is also used. So that's why it is important. So I'll share an assignment based on that. Even if you find it difficult, just attempt it, whatever you know. Don't take the help of Google or anything. I just want to see you are not being marked on these. Especially weekly tests will be there where you will be assessed and judged. These tests, these assignments are just for your practice and for me to know how much you have understood. So even if you're leaving a blank or you just write a doubt, so I'll know, okay, this is the doubt that you're facing, and I will at least know till how many steps your answers are correct. And I can then guide you for your board exams writing part also, just for that purpose. Now, see, when we have Gauss theorem is used when we are talking about a closed surface. So when you're talking about a closed surface, see, Gaussian surface is a surface that is chosen to make some surfaces closed that are open in nature. Like if I give you this wire, it has the charges present. Okay, all the charges are present from the wire, on the wire, and it is enclosed within. If this is present like this, so this is an open figure. Gauss theorem is not valid. We discussed in the last class that Gauss law is 1 by epsilon naught times the charge that is enclosed within the surface. The total flux is given by 1 by epsilon naught times the charge that is enclosed within the surface. So if the condition is violated, your law is inapplicable. So you'll have to enclose it first for the application to be executed. So if this is the wire and I just have this wire present, so I need to enclose it. So if best way to enclose a wire, straight wire, is just enclose it with the help of a cylinder. If this is present inside a cylinder, so now our cylinder, the flux through the total cylinder can be written as Q by epsilon naught. So at least our criteria will be saved and we'll be able to apply the Gauss theorem. Or if you have a sphere, for the spheres, it's best that you take another big sphere over it. So you have spheres, take big spheres over it. That bigger sphere will enclose your smaller sphere. So that flux through that bigger whole component will give you Q by epsilon naught. Okay, so this is what is present. Gaussian surface is there, so it should be closed. An electric field should be parallel or perpendicular to it. That's why we take cylinders. You will see it why. So let us practice one derivation at least. See, today's class is just of 1 hour. Just for today. The rest of the classes won't be such short. And class, keep your Thursday. No, I think now your time has been shifted from Monday to Wednesday. If there is a vacant slot, we'll put your classes for the backup classes that are left. Okay, because those portions need to be covered and they are extremely.
Which portions? I
Yes,
think we've
Aisha,
completed all. I think we've completed everything.
they are
Do you have anything left from the chapter?
from the part that we have done. We are left with. You joined later.
Okay.
Remember from that part, I think we discussed the properties, methods of charging. We were on the methods of charging, right? That part. because that is also important. See, one thing I tell you, this is a very basic chapter which will build your foundation for electromagnetism. So we'll not leave that portion. We'll do that also. And one class we'll have for integration and differentiation first, so that you don't face any error now after this. Because in your potential chapter, we'll need integration and differentiation. So as I discussed with you, I'll take your integration and differentiation first. But right now it's not utilized. So let's discuss this. Now see here. This is a surface area of a cylinder. And there are three sides that are present. This is the first, this is the second, this is the third one. Okay, now look here. If I take a perpendicular to this surface, this flat surface, because I told you, remember we discussed that whenever we have area, whenever we have to calculate the flux, we first calculate the area vector, because then only we will be able to calculate the angle between electric field and area vector. So suppose this is the flat part of the cylinder, upper circular flat part of the cylinder. So the flat part of the cylinder is this circular disc. Okay, so this one, see, if I drop a perpendicular to this, so look, this is how it will look like. This is how it will look like. So see, when I am extending it, this is n cap. Now look, the electric field is present like this along parallel, you can say, or perpendicular to the surface. Electric field is like this. And on the top, you have taken the area vector. So now what is the angle between area vector and the electric field? This is the perpendicular n cap. Your electric field is towards the right. What is the angle, class?
180 degree, because opposite of the electric field.
See. Electric field is along the right side. This is the electric. Okay, like this. Area vector is perpendicular to this surface, like this. So see, area vector is this, electric field is this. What is this angle formed?
90 degree.
90 degree. Okay. Now you're right. This angle formed is 90 degree. So when you have 90 degree ES, the formula of flux is ES cos theta. So ES cos theta, straight away when you have, see, this is n cap perpendicular, electric field is like this, angle is 90. Or look at the surface, this is the downward surface, same thing. Downwards also, here will be the n cap. So if you have the n cap present downwards, like this, electric field is this side. Again, angle is 90 degree. So when you have the flux as ES cos 90 degree, this is 0 due to the first surface and the third surface. So electric flux will be contributed by just the curved part. Okay, so that flux will be equal to E into S, E dot ds basically. E dot ds integral. So this is the electric field integral of ds. Now, electric field integral of ds basically means you have chosen a very small point. And the way we discussed it for the curved surface. So when you have this integral of a surface area like a cylinder, integral of ds means what's the total surface area for it? So total surface area of a cylinder is 2 pi RL. So this is one equation for flux. Now look, equation for flux is Q by epsilon naught also. Right, we have studied the equation for the flux is Q by epsilon naught also. According to our Gauss law. So this is second one. This is the value of flux E into 2 pi RL and flux is Q by epsilon. Now when we equate both of these, so E into 2 pi RL is Q by epsilon naught. Now it's a straight wire, so the linear charge density is preferable here. Linear charge density will be charge per unit length. So from here we can say charge is equal to lambda into L. So let's put it. E into 2 pi RL is charge is lambda into L by epsilon naught. So length gets cancelled. See what's the value of electric field. E is coming lambda by 2 pi epsilon naught r. This is the value of electric field due to a straight wire, and it's one of your important derivations of class 12. What is E? E is the electric field. What is lambda? Lambda is the linear charge density. Linear charge density. R is there, which is the radius of your Gaussian surface. This is not other surface. This is your radius of the Gaussian surface. Okay, when we're talking about the Gaussian surface. Radius of the, and here you know your Gaussian surface is a cylinder. So radius of the Gaussian surface. So this is how you have to write the entire derivation. And when you start the derivation, try to mention these things. Let E be the electric field. Full stories you should write in your exam when you have the derivations. And you will mention that y due to 1 and 2, your 1 and 3 surface area, your flux is 0. Tell me, is this clear properly? Is this derivation clear? Aisha and Marwa.
Yes, ma'am.
Aisha, clear to you?
Yes, ma'am. And we
Okay.
calculated it for the top surface, right?
What?
We calculated the electric field of the top
Flux, not
surface.
field. Flux.
Electric flux
field.
of the top surface.
Top and bottom we have calculated, and middle. See, this figure is made up of a cylinder. Okay, suppose this is a cylinder that is present. Now it has a top surface, it has a bottom surface, right? And this is the curved surface area of the cylinder present, correct? So when you have the flux, you will calculate the flux due to this circular part also. You will calculate due to this circular part also, and due to the curved part. So when you are calculating due to the circular part, what is happening? See, for the circular part is present like this, right? It is present like this. So area vector is downwards. See, a perpendicular if you put, it will act downwards. Electric field is towards the right. Electric field we have chosen. Why? See, because of the wire. Wire will let the electric field come out towards this side. So that's why this angle is 90 degree, as well as this top one also. When you are calculating due to this top surface, area vector will be like this, perpendicular to it, correct? Perpendicular to this top surface. So this is again 90 degrees.
Ma'am, in the third one, why is the electric field in the opposite direction? The second one?
Second one, this I am showing that even if you take it, see, electric field is on both the sides. If there's a wire present, this is a wire, electric charges are present on the entire sides of wire. So electric field, if I take it from this side, it will be on this side. If I take electric field on this side, it will be like this. So from both the sides, you will get 1 and 3 as 0 only. And for this, it will always be parallel. See, why are we taking 2? Why are we not taking 2 as 0? If I take perpendicular to this surface, to the curved part, see if the curved part is present. Now, if I take perpendicular, it will be like this. And this is the direction of electric field. Right? Perpendicular.
Ma'am, but in the case of area vector, if we take an area vector, we'll get different angles, right?
No, you will
It'll
not
be
get.
180.
That's what I'm saying. See, for this part, area vector will be this, n cap, angle 0 degree. For this part, area vector of this curved surface will be pointing this side. It will be 0. See, if you change the orientation of the cylinder, then only it will be 0. Because both the sides are curved surfaces and they'll have their respective area vectors like this. Now, if it was some sheet or some plain wire where only one side was filled with the angle, then this would have been 180 degree for the opposite side. That you are correct. But right now it's a wire with full charges accumulated. So area vector for the opposite side will have electric field also in the opposite side. So that's why here when you're writing, this is EDS cos 0 degree. Got it, Aisha?
Yes, ma'am.
Okay. Write it. If you still have anything to ask class, you all can ask. Okay, please write it down.
Ma'am, is that parallel side? The two lines?
This one,
Yeah.
yeah, parallel or perpendicular. Nabila just joined after 5 minutes. Right now, class 12th are having their classes. Okay, Nabila.
Okay, okay, ma'am.
Should I scroll down? Done?
Yes, ma'am.